here, and today we're going to take a look at flow simulation, what it is, how it works, and we'll get into a little bit of a hands-on presentation, a demonstration. So let's see here. As far as the agenda, we want to look at what fluid flow analysis is, why it's important. Then we're going to get into why SolidWorks flow simulation versus some of the other tools. We'll look at some real-life samples of problems that were solved using flow simulation, and then get into the flow simulation demonstration. So fluid flow analysis, or computational fluid dynamics, is just a simulation of fluid and heat transfer problems using a computer to do it. So it takes really complex equations and all those kinds of things, and kind of automates the process of figuring all that out using your computer resources. We can use it to check out flow of gases, fluids, blood, those kinds of things. We can also use it to extract forces. So if we have wind blowing on a sign, we can see what kind of pressures or forces are applied to a structure, and then we could run like an FEA study on those types of things.
Right.
So why would we want to invest in these things? And a lot of this is the same for a lot of softwares, to improve efficiency and performance. You may have been making something the same way for 50 years, and there might be one little thing you could change that would make it more efficient or, perform better, to improve quality. And always looking to cut costs, so any material we can take out of it's always a good thing. And to make sure we're providing the best possible solution to our customers. Faster lead time when we have to go out and create and have parts casted or machined or whatever, and then test it to discover that it's not really optimal, and then go back through that process can be pretty expensive and time consuming. So doing all this on the computer just helps to save time and money. So why SolidWorks flow simulation? Well, the big thing here is that it's integrated into SolidWorks, so there's not another interface that you've got to use. It uses all of the SolidWorks geometry, and anytime you make a change to SolidWorks geometry, it updates your flow simulation study. Also, when you have different fluid regions, it can automatically pick those up. And where this comes in handy is when you have two different fluids that are coming together, and or you have different regions that have separate fluids. For example, like a refrigerator, you may have Freon in one region and oil in another and air flowing around it in another. And you are allowed up to 10 separate fluid regions with different fluid material properties. And it's pretty easy to use. And as we get into the demonstration, you'll see that there's not a whole lot to it. More of the learning curve is in understanding, what loads to apply, or the material properties, and how to what to do with the results once you've got them. Actually getting results is not that hard. So just as far as some of the technical capabilities, this is not all, but these are some of the main features. You can do incompressible or compressible gas, so if you're doing liquids or gas, but we can also do subsonic and supersonic. This is catered more towards like aerospace, when you have rockets and airplanes and things that are going, Mach 1, 2, 3, and so on. We can do external and internal flows, so if you want to see how a fluid flows around something or how it flows through a system, kind of like how you would do with a pump with the internal flows. We also have the ability to do non-Newtonian flows, so it's more applicable for things like the medical industry, showing how blood can flow through a system. We can do automatic laminar turbulence solution with transition. We can do wall roughness, so if you're working with a smooth pipe, you're going to have different flows than if you have a cast pipe that has a little bit more porous wall there, and so we can set up a model for wall roughness as well to calculate pressure drops and turbulence and things like that. As I mentioned, we can have up to 10 independent fluids in one study. We can do free, forced, or mixed convections if you're interested in thermal. I know with the things you do, you're probably more interested with just the flow and the turbulence and those kinds of things rather than the temperature stuff, but that is also an option there. And radiation is another option that we can do just to help provide a more realistic thermal study. And these are all have the ability to be transient. So if we want to set up a variable load or a variable flow rate, say maybe you have a pump that starts off with a flow rate of X, and then after so many seconds it bumps up to a flow rate of something else. You can do those types of transient studies. Just as far as a few of the names, I'm sure somewhere in this list you'll recognize a few of the names. These are people who are, who have accepted this and use it on a day-to-day basis for analyzing their products. Just some examples of what people are using flow simulation for. It's used in electronics to understand heating and cooling and how to improve cooling efficiency of heat sinks and things like that. In automotive, there are a number of applications for understanding like radiators and intake manifolds, exhaust manifolds, those types of things. It's also used in HVAC if you want to understand ventilation, or if you add a fan to a room, how is it going to cool the room, where are the hot spots, and those kinds of things. In aerospace, it's used for aerodynamics to determine drag, to improve the efficiency of a wing design or something like that, to give a more efficient aircraft. And in machinery, just another example, being able to understand if you have a number of working components in a system, how does the fluid flow throughout the entire system, and are we getting the expected results? Bear with me just a second, and it appears that I have closed out of my PowerPoint. Let me just get that dude back up. There we go. So some real-life examples. The design challenge in this case, you can see we've got an electronic board inside an enclosure, and we want to understand how we can improve a heat sink. So in this case, we've got two different heat sinks, one with several fins that are all the same height, and one with evenly spaced fins, but every other fin is a little taller. Now, for somebody who may not have worked with heat sinks as much, you would look at this and be like, I'm not sure which one it is. But my guess is you've got more surface area over here, so you're going to have more cooling using this one. But we can test it to make sure and see if our assumption is correct. So we go in, we apply our heat sources and powers to all the different components, and we can see here that the temperature of the main chip using heat sink number 1 turns out to be about 94 degrees. With heat sink number 2, it's about 14 degrees cooler. And here with our flow simulation results, we can visualize this so that we can see most definitely they're both using the same color gradient for temperatures going from 50 to 100 degrees Fahrenheit. We can see the first heat sink has a higher temperature, the second one has a lower temperature, keeping the temperature of the chip cooler. This is just another cut plot to show the temperatures within the fins, kind of between them, how that is distributed. And so we can see that the heat sink number 2 has about a 17.5% lower temperature than the first one, so we would definitely want to go with number 2. Another example, here we've got a heat sink attached to a chip, but this time gravity is pointing downward, and we want to understand if we apply a heat shield to this, is that going to make a better or not as efficient heat sink? So in this case, we just apply the temperatures, set up our study, and extract our results for the chip, and we can see that without the shield, the temperature ends up being about 62 degrees, and with the shield, we get about 56 degrees. So about 6 degrees difference there by adding this shield. And when we look at the cut plots here, we can see that we have higher velocities of airflow, and the reason for that is hot air rises, we've got gravity turned on, and so as it's creating an airflow inside that shield, it's also cooling at the same time, improving the efficiency of how well that thing cools. And here you can see just a slice through the center of this guy. We have this air flowing through here as the hot air rises, and on this side we don't have as much of that airflow. We still have the same airflow between the fins, but now with this area enclosed somewhat, creating a little bit of a Bernoulli effect. All right, this just shows us our temperature distribution. Once we add this shield to the top of it, we're giving it more places for the heat to distribute to the ambient air, and so we're providing a more efficient heat sink design. So all in all, we get about an 11% decrease in the average temperature when we go with a shield versus without a shield. Our last real-life example here is an example of a flow of a medical device. what we've got is just a cup on the bottom here where the flow will enter, and we have a pressure, and it's going through a little screen. And once it goes through that screen, it turns and goes out this direction. And what we want to do is to allow the highest flow rate and have as little recirculation within the device as possible between two different designs. In design 1, we've got some triangle-shaped cuts. In design 2, we've got some circular cuts. So once we set up the study, run our study, we get our results, and we can see that the flow rate using the triangular cuts is lower than that of the circular cuts. Now, to take it a step further, we can see that they have pretty much the same pressure profiles between the triangular and the circular cut. As you can see, the maximum numbers here are about 15 and 15. The lower end's about 12 and 12. So pressure is not really that much difference. But as we get into our velocity cut plot, they're similar. You can see we've got a little bit higher velocity with the circular cuts. But one thing to note when you're looking at these results, the arrows represent the direction, but they also represent the magnitude. The bigger the arrow, the greater the magnitude of the velocity. Mm-hmm. Now, this is an important thing to look at when we're thinking about circulation or turbulence inside a system. When we look at the triangular cut, the flow comes in, but as it enters in and goes around this elbow, you can see that there's a bit of a recirculation, and it's a little bit larger area of recirculation versus what we have when we look at the circular cuts. It comes in, there's a slight recirculation, and it continues on its way. So as far as recirculation, the circular cut gives us a better result versus the triangular cut. So our results tell us that about 8 higher flow rate with the circular cuts versus the triangular cut. And I'm going to pause for just a moment. It appears John has entered the meeting. Hello, John. How are you?
Good. How are you guys doing?
All right. We're doing well. Well, we are slightly into our presentation. You've mostly just missed part of my PowerPoint. I haven't gotten into the software yet and done any of the demonstrations. So I'd say just sit back, relax, and enjoy. And as you have any questions, wait till I get to a good stopping point, and we'll pose those, and we'll discuss them at that time. Does that sound good?
Sounds good.
All right. Well, I will continue on. So that was really good timing. So we've gotten to the point where I'm going to get into SolidWorks and show you the flow simulation add-on and how it works, how to set up a study, and kind of the workflow of creating a study and extracting the results. So to do that, let me get into SolidWorks here. And what I've got prepared today is an intake manifold. And in this intake manifold, we can see that there are 6 outlets and there is 1 inlet. And so my goal is to understand if I have 1 inlet and I want to evenly distribute the what's coming into these 6 different outlets, how evenly is that being distributed with the design that I have currently? Now, the knowns before I set up this study is that I'm going to have a static ambient pressure on each one of these outlets, and I'm going to have a volume flow rate of about 0.05 cubic meters per second into this inlet. And that's all I really know, other than that the fluid is air. Now, SolidWorks Flow Simulation is an add-in to SolidWorks. To access these add-ins, you just come up here to the top of the interface and select your add-ins and scroll down till you find Flow Simulation. If you click this box on the left, it opens Flow Simulation for the current session of SolidWorks that you're in. If you click the box to the right, every time you open SolidWorks, Flow Simulation will be open at the same time. Now, this may slow down your open just slightly, but not a whole lot. So if it's something you use not as often, I would recommend leaving this unchecked. But if it's something you use every day, leave this checked. Now, when you turn the add-in on, it gives you a few things. You've got a menu item at the top where you can access all of the flow simulation tools. It gives you a flow simulation tab on your command manager where you can access the same tools. And once you create a study, it gives you a new tab in the feature tree over here that manages all of your input and your results. So before we get into setting up the study, one of the requirements for doing an internal flow simulation study is to have a completely closed off system. There can't be any holes to the outside. And you'll notice I've done a little bit of preparation for this. I have just some thin plates that have been added to my assembly to close off each one of these outlets on the manifold. But I'm going to show you two methods of closing a system off. Flow simulation has an automatic lid creation tool, and lids is just the terminology for these pieces here. So if I go to flow simulation in my menu and select tools, I can go to my create lids option here, and it tells me what I need to do in my properties manager. It says select a planar face that the opening belongs to. So I'll just zoom in on this area and click that face, and you'll see it applies that lid. As I rotate it, you'll see that the lid is going inward rather than outward. This is a little bit of an important feature right here because it has to go inward and outward, or just inward. It can't go only outward. If you do, you end up with a zero thickness where those two pieces of geometry meet, and that's not a good thing for flow simulation. So just keep that in mind. If you start to do a flow simulation that's an internal flow and it's giving you a beef about not being an enclosed volume, that may be why. And then here we can override the thickness if we need to. I'm just going to make this 1 millimeter and click OK. And it adds a part to my assembly and calls that part a lid. When I look in my assembly tree, you can see that there is lid 2. Now, another method for creating a lid, if I were to select this face and tell it to create a lid, it's going to cover up this outlet, but it's also going to cover up these bolt holes, which isn't really necessary as these are not pertinent to the flow of the system. So what we can do here is go to our assembly tab and tell it that we want to insert a new part. And you'll notice down here it says select the face or plane on which to position the new part. I'm going to click the bottom of this face, and I'm going to convert this loop to a sketch and then extrude that. Now you'll remember I told you it cannot go only outward. If I do, it creates a zero thickness geometry there, so I'm going to change my direction to be mid-plane. Now you'll see that it's both going in and out. And I'm going to set the thickness of this guy to 2 millimeters. There we go. All right, so I just exit out of editing that part, and we're back to the assembly level, and it looks like we have all of our openings to be closed off. All right, so now we're ready to create our flow simulation study. To do that, I'm going to go to my flow simulation tab, and I'm going to use the wizard to set this up. This is just another step that we go through that's quite easy. You just fill out the form, what you know, and you're done. So for this one, I'm just going to do manifold study, and I want to know outlet efficiency. And forgive me if I misspelled anything. I'm an engineer, not an English teacher. So I'm going to tell it to use the current configuration of this assembly and click Next. Here we just select what unit system we want to use, and we have a number of different ones. And this is not to say you're married to these. You can change any of these as you're applying these loads or pressures or things like that. In this case, I'm going to go with SI so that we're using meters, kilograms, and seconds. Now we need to tell it what type of analysis this is. In this case, we're doing an internal analysis, and I'm not going to worry about cavities without flow conditions because we don't have any extra cavities in our system. There's only one. And you can see here we can do heat conduction, radiation. We can make this a transient study. We can include gravity and rotation. None of those are pertinent to this study, so I'm going to leave those empty at this time. And here we have to select what fluid we're going to be using in our system. In this case, we're going to go with a gas, and I'm going to use air. So I just add that, and you can see that is my default fluid. Since there's only one fluid subdomain here, I don't need to worry about adding any others. But if you had more than one fluid subdomain, you could go in and add up to 10 fluids at this point. We're not going to worry about any thermal wall conditions or roughness of a wall. We're going to assume that this has a smooth interior wall. All right, this is just giving our initial conditions for the ambient environment. This uses, sea level, room temperature, everything that it would be in real life. So we can see our pressure here is what it would be, right inside your office there. The temperature is room temperature, and we don't have any pre-existing airflow around this thing. So I'll click Next. And this is the last step in the wizard where we set up our result resolution. And if we needed to change any of our mesh settings, we could do that here. But for the sake of the presentation, I'm going to go with the default settings for our mesh. And what you'll notice is once we finish the wizard, it gives us a flow simulation tree on the left side of the screen. And on the screen, it also adds a box. This box represents our fluid subdomain. Everything outside of this box is not calculated for. Everything inside of this box is what we're studying. Now, looking at our computational domain, that's that. If we needed to, we could pull that out and expand upon that. But in this case, all we really need to do is to apply an inlet and some outlets. So let's look at how we would do that. To do that, we would insert a boundary condition. And what you'll notice is most of the things that I'm going to be applying from here on out, I'm going to be using this tree and not so much using the menu items or the command manager up here. That's not to say that you could. I just find that it's easier to use these here. So I'm going to insert a boundary condition. In the first one, I'm going to say at this face, we are going to have a inlet volume flow. And that volume flow is going to be 0.05 cubic meters per second. So all you do is pick a face, assign a value, and click OK. And you'll notice as I assign that, it notates this with these arrows showing the direction, and it colors it red as it is an inlet. Now let's take a look at our outlets. We do these the same as we would an inlet. I just insert a boundary condition, select the face, and this time I'm going to do a pressure opening and tell it that this is just a static pressure, and it's going to use just a standard environmental pressure that we would have in your office. So I'll click OK to this. There's one. And I'll repeat that process for the others. Last few here. So there's not a whole lot of manual input when you're creating these studies. It's just a matter of picking and clicking. All right. So now I have all of my outlets assigned, and you'll notice that each one of these has a different colored arrow so that you know that it's an outlet and that it's a pressure opening. The arrows are going both directions. All right. So now that we have our inlets and our outlets assigned, the study is pretty much set up, but we need to tell flow simulation, why are we even running this study? What is our goal? And so as I go back to my tree, we'll see here we have our goals. I want to insert a surface goal. And I'm going to select this face, and I want it to tell me what the volume flow rate of this face is when I run my study. And I'm going to change the name of this particular goal to inlet, and click OK. So now I have a goal for that face. Now the next thing I want to know is what is the volume flow rate for each one of these openings. So to do that, I'll right click on my goals, tell it to insert a new surface goal, and I'm going to click each one of these. So I don't have to do this one separate. I can pick them all in one go. And you'll notice there's a little box right here. It says create goal for each surface. That way it'll break each one out individually. And I want to find what the volume flow rate is at each one of those. And I'm going to change the name of this goal to outlet. And click OK. All right, so now I have my inlet flow rate and my outlet flow rate. But what if I'm interested in what the overall flow rate is across all 6 of these little outlets right here? We have another type of goal, which is called an equation goal. And the way this works is you just select any of these previous goals, and you can add equations. So I want to know what this plus this plus this plus this, and so on until we get to the end. So it's going to give us the sum of all of the pressure openings for those outlets. And I'm going to call this sum of outlets. And click OK. So now I have an equation goal set up to tell me what the overall volume flow rate is across each one of those. Now we're ready to run the study. So I just go up to the top of my tree here and select Run. And one cool thing about flow simulation, if you are set up in a network environment, this study isn't going to take very long, but some of these transient studies that are pretty heavy duty, you have the ability to add more computers so that you can process with multiple processors across your network. This comes in real handy when you're working on really heavy simulation studies because it decreases the time it takes to solve. In this case, I'm only going to use this computer and tell it to run. Now, when I select Run, it pops up a new program here. And what this is showing, it shows that it's preparing the model, and then it's going to create a mesh for that model, and then it's going to solve for each one of my goals. So right now it's capturing the mesh, and it gives us a progress to show what's happening here. Now, I've gone ahead and inserted a pressure plot, so as it's solving, we can see what the pressures are and how they develop in the system as it reaches an equilibrium. And so it gives you a progress bar down here on the bottom to show you how far of a progress it's got. And this one is actually fairly accurate. For those of you who use Windows, a lot of the times you'll look at a progress bar and it'll say there's 5 minutes, and then you'll come back in 5 minutes and it says there's 8 minutes left.
Yeah.
This one's pretty accurate. It doesn't give you a time, but the progress percentage is pretty spot on. Another thing we can do is I can go in and tell it to look at a goal plot and tell it to add all of my goals and see where we're at converging on each one of our goals. So we have converged on all but one of these. The one that it has not converged on yet is the third outlet, and so it's working on that guy. And in just a second, we should be able to see our results. And there we go. So we've achieved a solution for each one of those outlets and also our equation goal. So I'm going to close out of the solver and take you back into the SolidWorks interface. So at this point, we have a whole new list of things that we can look at. This is our results. When we look at the results, we have goal plots, which can be Excel spreadsheets. I'll show you that one first. If I insert a goal plot, I'm going to select all and then tell it to show. And what it tells us, our inlet flow rate, the maximum value is 0.05. That makes sense, right? That's what we predefined it to be. Now, when we look at each one of the flow rates for the outlets, it gives us the maximum value. So we can see at each one of those outlets what that maximum flow rate is. And then when we look at the sum of the outlets, we've got that value here. So that gives us all of those, all of the values for each one of the outlets plus the sum here. We also have the ability to export this out to Excel. So if you need to take this to an R&D or a Q quality meeting, something like that, and they need data and charts and things like that, you have the option to export to Excel. And here's that goal plot and what it looks like. And it gives you a new sheet for each one of the goals that you created. So if I look at my volume flow rate, it shows me this is the volume flow rate over the number of iterations. At first, it gradually applies that load, and then once it reaches equilibrium, it shows us what that value is here. All right, so that's just a little bit on the goal plots. Now, we do have some other pretty handy tools like flow trajectories. If we want to understand how the air flows, if there's any recirculation, what does that look like? I'm going to right-click and insert a flow trajectory plot, and I'm just going to select these faces for the outlet, and I'm going to do 120 pipes to spread across all 6 of these, and I want to see, let's say, maybe what the velocity is. So as I click OK, it goes in and creates 120 points spread across each of those faces, and the pipes show the actual flow. And you can see that there's some recirculation in each one of these little guys. As we get towards the end, as this is a gradual turn and it goes straight down, you can see there's very little, if any, turbulence in this last one. But these first ones, because it has to make that sharp turn, we can see what kind of turbulence and how bad that is. But it also gives us a color chart to show what the velocity is in meters per second. So there's a little bit of a dead spot right here because that velocity that's dark blue is 0 to 1 meters per second. And so it's just kind of got a little dead spot inside these first three. All right, I'm going to show you another neat thing about this. With the flow trajectory, we have the ability to animate these. If you wanted to put this into a PowerPoint presentation, what this will do is it shows an animation as the air flows through the system, how it goes into each one of these separate items here. And as it goes to the end, you can see each one of those and how it goes from beginning to end. All right. Another handy plot, I'm going to turn this one off. And we're going to look at a cut plot. In this case, I'm going to use the top plane for my cut plot, and you can see that it cuts through this part through each one of those little legs hanging out and also the main cylinder. And I want to understand what the pressure is. I click OK, and it shows me where my maximum pressures are. And right out here at the end, where you would think it might be, you've got air coming in straight and it hits a roadblock and has to turn. We have our highest pressures down here on the end, and it gives that to us in pascals. Now you can change this if you are interested in, let's say, velocity, and click OK. You can dynamically change this to show you any of these items. So maybe temperature is not really that big of a deal. So velocity and pressure would be my main two things of interest. So just another little plot there to visualize what's going on inside this system. And you can put any number of cut plots. If I wanted to apply another one, I can insert another, tell it to use the top plane, but then offset it just a little bit. Let me say about, there we go. And that's going to put it down a little lower. I'll click OK. And so now we've got multiple cut plots if we want to see what this is doing in different areas of our system here. All right, now we also do have an option here to create a report. And what this report does is it gives you the ability to insert any pictures into your report, like these types of plots. It also gives you the ability to insert those Excel spreadsheets so that you have all the data that you would need for your goals, and combines them all together with those images and all the result plots that you've created. So you've got it all in one handy file there for you.
Now, Tim, let's assume that this is an intake manifold for an engine, and this simulation is showing you it's showing you flow to all of them simultaneously, where in reality you would have only one open at a time. Is there a way to simulate?
Yeah, what you can do there is where you have, you can create different configurations of this particular study. So right now it's showing all 6 open. At this time, you can create a configuration where maybe 1 and 3 are open and the rest of them are blocked off. And so you
right, I was wondering if you could do an animation showing as each one opens at a certain time, what would happen to the entire system flow, or is that beyond the capability?
That's a little beyond the scope of what we can do here. We can set up a situation, we can run it as such, and then we can set up multiple configurations to show what the flow would do at each setup. But going dynamically as one opens and the other one closes, that's a little beyond the scope of what flow simulation does.
Okay. I would think that would be very important to see as one opens and another one closes, the backflow and turbulence causing by the one closing, and the
Now, one thing you can do is you can have a dynamic pressure. So here, where this is just the environmental pressure, you could say, you know, the pressure is X, and then you can change it to be any other pressure over time. So that might be a way to do what you're talking about there, to change what the pressures are at each one of these outlets so that it simulates the same type of thing.
Yeah. Okay. It's just a thought, you know, looking at the at what you're doing.
Absolutely, and that definitely makes sense. This is just pretty much testing it as is without being attached to a motor or an engine, and you know, seeing how it flows through each one of these. But I would think that putting a variable pressure at each one of these openings would be able to simulate what you're talking about there.
Well, the simulation came out pretty much as I expected it, with those sharp corners and a smooth corner at the end one. I was expecting there to be turbulence and also a smoother flow at the end, which it really showed.
Sure. And I've been surprised in some of the simulation studies that I've run with flow, you know, especially like in some of these areas, some of the subtle changes that you can make to some of the geometry in this area can really affect, you know, the amount of turbulence that you've got there, whether it increases or decreases. And sometimes it would be the exact opposite of what I would think when I make a change. And so that's why, you know, something like this is pretty handy, so that you can do a lot of what-if scenarios without actually having to create a whole bunch of different prototypes to test that out.
I think I would look at it as starting out with a larger opening at the inlet end and then having smooth curves at each one of the legs in the direction that the inlet was coming, similar to the one you have on the end.
Right, right.
And then a constantly reducing cross-section as it went from one end to the other would allow smoother flow. But anyway, that's just my thoughts.
Right, and that comes back to the, okay, we have some results, now what can we do to make it better? We make a change, we test it, we validate it, and we can see how much better, and to justify, you know, tooling cost or material cost to make that change in the product. So it all goes back to that whole side of problem solving and having a tool that can quickly give you the answers to what if.
So what's involved in making a change? Obviously, they have to remesh it.
I'm sorry, your volume's a little low. What was that question?
Okay, yeah. I was wondering what's involved in making a change. Does it have to remesh after each change?
It will. Anytime you make a change to the solid geometry and or the fluid subdomain, it would need to remesh.
Okay, thank you.
Mm-hmm. Well, this is all that I have prepared for this presentation as far as the SolidWorks side of it. This was meant to be a kind of an introduction to flow, to show you what it is, how it works, how to set up a study, how to define your goals, and then how to view the results. I would be more than happy to answer any other questions that you guys have at this point.
Yeah, I'm of course, being in the pump industry, I'm mostly concerned with flow in and through a rotating impeller and the interaction of that flow with a stationary enclosure, and that's what I'm really very important to us. And the main objection we have is that although I have seen a simulation that shows that, I really need to know, how is it done, and is there anybody that can train me to use it? Because let's face it, the cost of SolidWorks, we only have two seats, but we're talking about $3,500 for a 3-year commitment on 2 seats. And for flow simulation, it's what, $17,000?
Right.
So it's awful large investment from our point of view, So it's really got to pay for itself, and unless it can do what we need it to do, we're not interested.
Right.
Just way too much money, and I guess that's what I need to see is a simulation of an actual pump running and showing how it would analyze the flow inside a pump, and so that I could take, and I think I told you this one, recently I was redesigning a pump that we already had that had some issues with it, and the main issue was that the company that made the tooling and made the first batch of castings went out of business 4 years ago, and the tooling was no longer available. So rather than going back and redoing the exact same pump, since we had some issues with it, it was taking a look at seeing what would happen if we changed the impeller design. And when I ran the numbers that are from Bart